Okay, so let's continue this little journey in current or in with electric circuits. Okay, so current density, right, is the amount of charge per unit of time that flows through a unit of a chosen cross section. Okay, so if you think about when we did electric charge and we looked at the surface density, right? This is almost the same idea, right? So it's the amount of charge that is flowing through a unit area for a given amount of time. The symbol is J, and the unit is coulombs per square meter. Okay, and so the reason is because it's coulombs per square meter is because we're doing charge per unit time. Okay, that flows through an area. Okay, so current, which is a scalar quantity, is related to current density, which is a vector, with this equation. So I equals the integral of J dot dA. Okay, and so and again, you don't have to kind of worry yourself about this equation because it's just simply going to be JA, right, in the end, right? So I equals current density times area. Okay, and so when you look at it, so J is our current density. It's a vector perpendicular to the surface area or the element of area dA. Right, and then so current density has the same direction, right, as the velocity of the moving charge if they are positive, and opposite if they're negative. So if I have if I say I have a wire and I have it flowing this way, right, as long as if this is a positive flow, my current density will be in this is in the same direction, right? Because it's like, okay, I'm gonna see how much is flowing through that point, right, during any given time. Okay, now because they're moving, they're moving with a velocity. All right, so when an electric field is established in a conductor, the charge carriers assumed to be positive acquire what we call a drift speed. We call it V sub D, right? So the drift velocity or drift speed, right, in the direction of that electric field. Now, to calculate the drift speed, you're going to use the equation J equals NE times velocity, right? So times the drift velocity. So this current density equals NE, and this product NE, right, the unit is coulombs per meter squared, and this is what we call carrier charge density. And this is something that you would have to determine for most of them, or a minimum the N, because E is our elementary charge, right? This little N is related back to molar mass, so it's going to be Avogadro's number times the density of the material times the molar mass of the material. Okay, and we're going to do an example where we actually have to do this calculation. All right, you can substitute all that into the J formula there and get a kind of like a bigger version of the J formula if you wanted to use that. But so let's do a couple examples, solving for drift velocity and so forth. Okay. So the first question here says, the current density in a cylindrical wire of radius 2.0 millimeters is uniform across a cross-section of wire and is J equals, oh, I gave you the wrong unit for J earlier. So let me go back up here. So J is not coulombs per meter squared, and I apologize for that. It's actually amps per square meter. Okay. And so what is the current through the outer portion of the wire between the radial distances of R/2 and R? And then suppose instead that the current density through a cross-sectional area is with a radial distance of R as J equals AR squared, in which A is equal to 3.0 times 10 to the 11th amps per meters to the fourth, and R is in meters. What now is the current through the same outer portion of the wire? Okay, So basically, here's what we need to do, right? For part A, we want to find the current between R2, right? So here's my wire, okay? And it's like I set up this imaginary, kind of limit. So here's R2, or R over 2, and then R. And what we want to do is we want to find what is the current that is flowing through that portion of the wire, okay? So for part A, we're looking for what is the current through the outer portion of the wire, right, between that distance. So what we need to do is we need to figure out how much area is right, in what I kind of am coloring right now. So we need to find our area that we're looking for. So it's going to be the big area, so pi big R squared, minus the small area, which is going to be pi times R over 2 squared. And so that's going to be pi R squared minus pi R squared over 4. And so it's like 1, right? So it's going to be, let's see, 1 minus 1/4, really. So it's 4 over 4 minus 1/4 is going to be 3/4 pi R squared, right? So that's going to be our area. And so now we can go through, and we can plug in numbers here. And so they tell us that big R is 2 millimeters. So we're going to say 3/4 times pi times 2 millimeters, but we need that in meters. So it's 2.0 times 10 to the negative 3. And so that gives us an area of that we're looking for, concentrating of 9.425 times 10 to the negative 6 square meters. Okay. And now that's going to go, so we're going to use J equals I over A. Okay. And then, so we're looking for current, and I equals JA. And now we just simply do J, which is 2.0 times 10 to the 5th, times the area that we're looking for, which is 9.425 times 10 to the negative 6. And we get a current that flows through that portion of the wire of 1.88 amps. Okay. Now in part B, because here's the hint again, right? I keep telling you guys that if you see a function that varies with, or that is not constant, you're going to have to use the calculus now, okay? And so we're going to use the calculus equation. So we use current is equal to J dot dA. But again, you don't have to really worry about yourself with all these vectors and so forth. We're going to make the assumption that the dA is perpendicular. So we don't just simply to say that we're going to find the integral from R over 2 to R of J dA, right? Now, what happens, right? How can I start translating this? Because unless we have dA, and the way you think about it is what is actually changing with respect to whatever, it's the area, right, is changing with respect to the radius. And so we're going to do, if I just keep kind of writing through here, J is going to be my AR squared. Okay, that's what I circled up there in the question. And we know the area is going to be 2 pi R dr, right? Because the radius is going to change with respect to, as we go, right? So what is really going to change about that area? The 2 pi R, okay? And in this case, we are looking, so it says the same outer portion of the wire, okay? But again, that's what actually ends up changing, right? Is kind of the length of the wire, okay? And so I can now simplify my integral here. I can pull out the 2 pi and the A, those are constants. Okay, I got R squared and R, so it becomes R cubed dr, right? And so if we do our integration rules, it's n plus 1, to the n plus 1 over n plus 1. So I got 2 pi A over 4, right? Because the over n plus 1 just gives me a 4. And so this just becomes R to the 4th, right? And we still have to evaluate that from R over 2 to R. Okay. And now I'm going to say 2 pi A over 4 times big R to the 4th minus R to the 4th over 16, because I have to do R over 2 to the 4th. Okay. And so that ends up being, so this is like 16 over 16. So what's inside ends up being 15/16 big R to the fourth. Okay, let's see if I can do any cancellation here. This 2 cancels that. That becomes a 1, that becomes an 8. So 15, or 4 times 2 is 32. So it's 15, or excuse me, I wrote a 3. So it's 15 30-seconds pi a r to the fourth. Now I can just plug in numbers, okay? So I got 15 over 32 pi times a, which is 3 times 10 to the 11th. Another reason why you know it should be to the fourth is because look at that unit for our a, it's to the fourth, right? And then I have 2 times 10 to the negative 3 to the fourth, right? Because our big R is still 2 millimeters. And so what kind of current do I get here? I get a current of 7.06 amps. So you can see if I change R, or if I change J with respect to R, I get a little bit more current that is flowing through that time, or through that period, that wire. All right, last example problem in this section, right? This says, what is the drift speed of the conduction electrons in a wire copper with a radius of 900 micrometers when it has a uniform current of 17 milliamps, assuming that each copper atom contributes 1 conduction electron to the current and that the current density is uniform across the wire's cross-section. So the first thing we need to do is really figure out how many electrons per cubic meter are there that exist in this sample of copper, okay? So we got to find that N number, right? And so as I mentioned before, it's N, or Avogadro's number, times the density of copper times the molar mass of copper. Okay, so Avogadro's number, 6.022 times 10 to the 23. The density of copper, don't worry, I had to look it up, is 8.96 times 10 to the 3 kilograms per cubic meter. And then the the molar mass of copper is 63.54 grams, or 65.34, or 63.54. Switch those, times 10 to the negative 3. Again, if this is going to be on the exam, they should give you the molar mass, they should give you the density, because I took this from a textbook, I had to look that information up. And so it tells me that there are 8.49 times 10 to the 28 electrons, right? Really per cubic meter, because if I go through, this is particles per mole, this is grams per, or kilograms per mole, right? And this is in kilograms per cubic meter. So it's still electrons per cubic meter is my N number, okay? And so now I can use my drift equation formula. So J equals NEVD. And so I'm looking for, and that, one thing to note is that they give me a current, right? And they give me information to find a radius, an area. So I do have to substitute in the formula for J, which is I over A, so NEVD, right? And I'm looking for V sub D. And so I simply solve, it's going to be V sub D equals I over A N E. Okay, but A is pi r squared, so it's going to be I over pi r squared N E. And now I can plug in numbers, having to remember to convert, right? Because milliamps and micrometers. So it's going to be 17 times 10 to the negative 3 amps, pi times 900 times 10 to the negative 6 squared times N, which was 8.49 times 10 to the 28th. I'm running out of room. I'm going to write it down here below it. And charge 1.6 times 10 to the negative 19th, right? So all this here is multiplied together. And so my drift velocity for these electrons will be 4.92 times 10 to the negative 7 meters per second. Okay, so there's a drift velocity calculation, all right? Now the next thing we're going to start talking about is resistance and resistivity, right? And we're going to start building our way to talking about circuits.